So this is going to be a different demonstration of LeChatelier's principle. So I'm going to start out with this solution of cobalt chloride, an ionic compound that is actually dissolved in ethanol. So it is not dissolved in water. Right now there's no H2O, and you can see this sort of brilliant blue color. And that is the color of the tetrachloro CoCl4 ion. It's a complex ion. It's cobalt 2 and 4 chloride minus ions together in what's called a complex ion. That's why it has these brackets around it. And the whole thing has a -2 charge. So it's a special kind of a compound we haven't really talked much about. But I'm going to put some of this in a couple test tubes. Cobalt is one of the transition metals, and I've talked about before how transition metals often are brilliant and beautifully colored. And this is an example. Cobalt, there's even a color named after it called cobalt blue. Cobalt in this state is often used in making glass, deep blue glass, colored glass. So I'm going to just add some in there. And the question is, what's going to happen if I add some deionized water? So I'll leave one of those there so you can just look at that blue color. And then I'm going to take a dropper here that's got a bunch of deionized water in it. I'm going to take one of these test tubes. See if I can't hold it a little bit closer. And just watch what happens as I add some water to it. Just add a few drops so you can already see what's happening. Turns this nice pink color. And what I've done is I've set up an equilibrium between the CoCl4 and water to produce this pink counterpart, cobalt hexaaqua ion. That's 6 waters that are complexed with a cobalt 2 and then there are some Cl minuses. So you can see the dramatic difference between these two. And I just want to show you how we can push the position of equilibrium back and forth by doing things like changing the concentration of different ions in the solution and by changing the temperature. So one thing we could do is ask the question, what if I added a bunch of chloride ions? And how I might do that is I'm going to add some concentrated hydrochloric acid. So this is essentially a lot of Cl- ions that are dissolved in water at a very high concentration. And so while I'm adding a little bit of water, the main effect is going to be adding chloride ions. So let me just show you what happens here. This one's kind of fun. If I just add one drop at a time, you can see it turns that blue color. Mixes in, and it's moving back to the blue. So I'm adding a product and it's shifting it back to the reactant side. If I add a little bit more, now I've moved it back to the blue. I can bring this around again by adding some more H2O. So you can see now it's sort of an in-between. It's a mixture of both the blue and the pink form, sort of a purpley color. I can add some more water. I can drive this all the way to the right. Well, I can just play this game all day. Add some more Cl-. I could also do this by adding sodium chloride, which if I can find some, I'll try and show it to you. But what I'd like to do is see if I can push this pretty far to the left. And I'm going to bring it back just a hair. Just somewhere back in the middle. So there I am. I'm not fully pink. I'm not fully blue. And I'm going to change the temperature. So we're going to see which direction this is driven by a change in temperature. On your left is some boiling water, and on your right is some ice water. So let's watch as I pop this into boiling water. that is pretty cool. You can see it turned a blue color really quickly. So this beautiful blue. And so then the question is going to be, what will happen, do you think, if I put it in some ice water here, over here on the right? And just putting that in ice water. Give it a little stir. It's like making a martini. You can start to see the change already. So it didn't happen instantaneously. It takes a while for the heat to be drawn out. But you can see it shifted back over to be pink. So what I want you to think about is this reaction exothermic or endothermic based on the direction of shift? So just watch again. I'm at some position of equilibrium. I'm going to change the equilibrium constant by popping it in hot water. If I was a better cinematographer, this would be a lot better, but I think you can get the idea. And then I'm going to just bring this back to room temperature again and show you one more example of LeChatelier's principle. Alright, so the first time I added some Cl- by adding concentrated hydrochloric acid. But now I want to ask the question, is there a way to take some chloride out of this equilibrium? And I can do that by adding silver ions. And silver ions, Ag+, will react with Cl-. Not the chloride that's bound up with the cobalt, but these free chloride ions over here. And they'll take them out of the reaction. And so before I do that, you can think about it. Which direction is this reaction going to shift if I add some silver nitrate with silver ions? One hopes. All right, here comes the silver. You can see it's getting pretty pink. How could I drive that back? Let's see if I can add more chloride and push it all the way over to blue. That's pretty cool. So now we're in that sort of in-between state. It's actually getting a little dilute, so I'm going to actually go back and start over with this one. So I'm going to take this fresh cobalt in ethanol solution. I'll add a little bit of water. Too far. So that's okay. I'll drive it back to the left with some chloride ions. There we are. Let's really push it over there. So we're firmly, equilibrium appears to be lying to the left. There probably are some pink cobalt H2O6 ions in there, but there's a lot more cobalt CoCl4 2- ions. But I want to see if I can remove some chloride. So I'm going to sequester them or bind them up with the silver. And they should just, probably don't need too much more than that. Nope, still some in there. Let's take them out of that equilibrium. Still blue. Things are looking good. You can see the color change as predicted. So there we're getting into the pink. So let me just give a good squirt. So there you can see this nice pink color. So the silver ions have reacted with chloride ions that were part of this equilibrium, taken them out of the reactive equilibrium, and according to LeChatelier's principle, this equilibrium had to shift to the right to undo that. So I wonder what would happen if I put this equilibrium that lies to the right now in hot water, which appeared to make it turn blue. Will this make that happen? Looks like it does it. So even removing chloride ions with silver is no match for changing the equilibrium constant K by changing the temperature.